I believe this is the third video of the SOL review going through the 2015 SOL. This problem says if 89.6 joules of heat, let's stop right there. I know this is going to be something involving heat. And one of the main equations that you think of when you involve heat, if you're going to think of anything else, is Q equals mc delta T. We're going to see if that is going to be a valid equation to use in this example. So if 89.6 joules of heat are needed to heat 20 grams of iron from 30 degrees Celsius to 40 degrees Celsius, what is the specific heat of iron? Finally, we use that equation that we've been talking about so much. I've got a couple of values though. I've got joules of heat, mass of iron, and a change in temperature from 30 degrees to 40 degrees Celsius. What is the specific heat of iron? This is the equation for specific heat capacity. Q equals mc delta T. Let's go through and see if we can actually use this, or if it were like the last example where we couldn't use it because there was no change in temperature. We have joules of heat, that is Q. We have mass, that is M. And we have a change in temperature, which is delta T, 10 degrees. It went up by 10 degrees. We are actually solving for the specific heat capacity. So let's solve for the specific heat capacity by not violating any algebra rules. To get the specific heat constant alone for iron, in order to solve for it, we need to get the C variable by itself. That means we're going to divide both sides by m delta T. Doing this, we get Q divided by m delta T equals C. And we're going to go through and make sure everything else is standard. Look at your units, always look at your units because they can tell you a bunch of things. Joules is actually going to be on the top in the units for specific heat. Grams is going to be on the bottom, and the degrees Celsius will also be on the bottom. You don't have to convert to Kelvin. If you were to convert 30 degrees Celsius and 40 degrees Celsius to Kelvin and then take the difference between the two, it would still just be 10 degrees. Our mass is in grams, not kilograms. That's good. And much more commonly, sometimes you'll see heat in kilojoules or maybe calories. We want to make sure that they're in joules for this case. So Q is 89.6 joules. The mass is 20 grams. And then the change in temperature is 10 degrees Celsius. And when you do those, I'm going to get, I think I memorized just from use the specific heat capacity of iron, but I'm going to work it out on my calculator. 89.6 divided by the quantity 20 times 10. Make sure that you're using parentheses. When I did this in my calculator, I did 89.6 divided by parentheses 20 times 10. And I got 0.448. And these are the units. And if you actually look really carefully at the units and you're completely lost, the units actually tell you exactly what to do. In this example, the units say take the joules, take the grams, take the degrees Celsius, and then divide them just like this. But please remember to use parentheses so that your order of operations stays true. Which of the four substances on this pH scale is slightly basic? As far as acids and bases go, you probably remember from 8th grade or whenever you took physical science, and certainly from this class, that the dividing line, and I guess I should really be using purple, the dividing line for acids and bases is 7. If you are below 7, you are an acid on the pH scale. Remember that the opposite of pH is pOH, and all the numbers are opposite up to 14. So on the pH scale, acids are below 7, bases are above 7. The closer you are to 0, the more acidic you are. The closer you are to 14, the more basic you are. If this is slightly basic, you're looking for something that is on the 7, that is greater than 7, but not much greater than 7 relative to something else. So calcium hydroxide is a stronger base than human blood, which is considered to be slightly basic because it is about a 7.5. So human blood would be considered slightly basic. Suppose this question had asked, which of the 4 substances on this pH scale would be slightly acidic? You've got 2 things that are acidic. You've got whole milk and lemon juice. If you've ever drank whole milk or lemon juice, whole milk is not sour unless it's spoiled, but lemon juice is considerably sour. So whole milk would be the one that is slightly acidic. And then lemon juice relative to whole milk would be highly acidic. This asks, which element will most likely form covalent bond with fluorine? Here's how we think about one of these more analytical questions that has no math, but you still really have to think about it. Fluorine is a nonmetal. That is helpful because we're talking about bonds here. And if you have nothing else going on in your head about the bonds, you need to remember that you have ionic and covalent as far as like the big 2 that you have to remember and distinguish. Remember that covalent bonds are going to be 2 or more nonmetals. And then ionic bonds are going to be a metal oftentimes and a nonmetal. Remember that for ionic bonds we have that one exception, which is ammonium. That's why the better word to use instead of metal would be cation. But anyway, back to the problem. It says which element will most likely form covalent. That means nonmetal meets another nonmetal and they share electrons. They share their valence electrons with fluorine. Let's go through these. Carbon. Carbon and fluorine, they hang out sometimes in a compound such as carbon tetrafluoride. This is a nonmetal and a nonmetal. So carbon's a pretty good option for right now. Potassium can make bonds with fluorine, but potassium's a metal, fluorine's a nonmetal. So instead of being electrons shared, it would be electrons stolen. Fluorine would accept, potassium would donate. Potassium, being a metal, would not form a covalent bond. It would form an ionic bond. Neon is a noble gas. Noble gases don't like to bond anyway, so no bonding. They are not reactive, so we're going to say neon is very unlikely to form a bond with fluorine. Although neon and fluorine are close, that is what the test makers would be wanting to see if you understand that the closeness of 2 elements has nothing to do with how likely they are to bond. Tin is a metal. You could form a compound like tin 2 fluoride, but that would also be ionic. So the only one that makes sense is carbon, because carbon is a nonmetal and everything else is either a metal or doesn't want to bond. The physical process of evaporation involves. So let's talk about what evaporation is again. Evaporation is a form of vaporization where a liquid becomes a gas, not necessarily at room temperature or not necessarily at the boiling point. So in order for evaporation to happen, you don't form ions. When water, that is a liquid, turns into a gas, vapor, you're not forming water ions. An ion would involve the transfer of an electron. Electron sharing. That isn't true because electron sharing is covalent bond formation. Transferring valence electrons would be ionic bond formation. Overcoming intermolecular forces. Remember that intermolecular forces are the things that are the forces between molecules that keep them in a certain phase, and they have to be overcome, not necessarily broken, but overcome in order for a phase change to happen that involves the addition of heat and the spreading or the increase in entropy of matter. So let's draw out water. Water is shaped in a bent Vesper geometry, and in the presence of other waters or ammonia or other things that can do hydrogen bonding, there will be some attraction. I meant to do that in orange. There will be some attraction between the hydrogen in one atom and the oxygen the hydrogen and the oxygen in two different molecules of water. In order for water to vaporize or evaporate, you have to spread those water molecules out even more from the liquid phase, because gases are more spread out than liquids. In order to spread them out, you have to break or overcome those intermolecular forces. That way, this water molecule can fly away this way, and this one can fly away this way, and they're spread out gases. So a liquid is going to have really close particles that take the shape of the container and has a certain volume but no shape of its own. And then a gas would be the particles are now separated and have very little interaction with each other, and they're flying off in different directions. How many moles of oxygen are in the chemical equation when balanced using the lowest whole numbers? Lowest whole number coefficients, remember that they're integers. Whole numbers would not be 1/2 or 0.3 or square root of 2. Whole numbers are the normal counting numbers, 1, 2, 3, 4, and so on. In some chemical equations, you may see half numbers, and if you were to take AP chemistry, you may see half numbers in like heat of formation and stuff like that. But for a reaction where you have to just balance it, you want to deal with whole numbers only. Remember that for a combustion reaction, which is going to be some carbon-based compound that burns in the presence of oxygen to create carbon dioxide and water. For a combustion reaction, the easiest thing to do is the Cho rule. So I'm going to rewrite this. It's going to be C2H4 plus O2 yields CO2 plus H2O. So the Cho rule is going to be important for us here. The Cho rule says balance your carbons first, then your hydrogens, and then your oxygens. So there are 2 carbons on the left. I want 2 carbons on the right. Carbons are happy, move to the next letter, which is hydrogen. There are 4 hydrogens on the left. I want 4 hydrogens on the right. Once your right side is filled in because of the C and the H, you need to stop right there and count up your oxygens. I have 2 times 2 is 4 oxygens, plus 2 times 1 is 2 oxygens. I have a total of 6 oxygens on the right. In order to get 6 oxygens on the left, I could put a 3 here, giving me 1, 3, 2, 2. So it asks how many moles of oxygen are in the chemical equation when balanced. The answer would be 3. Always go back and check because people can make mistakes. There are 2 carbons, 4 hydrogens, and 6 oxygens on the left. On the right, there are 2 carbons, 4 hydrogens, and 4 plus 2 is 6 oxygens on the right. This is a cathode ray tube. If you remember about when we learned about the scientists and atomic theory development, while English physicist J.J. Thomson was carrying out experiments on cathode rays, he was able to determine that the rays consisted of particles he called corpuscles. These particles were later named Now, here's a couple of ways to think about this if you don't remember the history of it. Negative and positive charges, anodes and cathodes, that sounds a lot like electricity, because this is actually what this really was, kind of like a neon lamp, so to speak. And what moves in an electric current are something called electrons. Remember that J.J. Thomson effectively discovered the electron, and then there was Millikan and some other people. But electrons are what moves in electricity. Electrons are easy to see because they're the ones on the outside of the atom that can actually do the jumping from atom to atom. Remember that protons and neutrons stay pretty intact in the nucleus itself. So that is why the electron was first discovered. And remember that J.J. Thomson had the plum pudding model because he had an idea about electrons, but he had no idea about protons and neutrons and what exactly those other particles were. So the first particle discovered was the electron. In the Haber process, nitrogen and hydrogen are directly combined to form ammonia, which illustration contains the stoichiometric quantities of the reactants for this reaction. Here's how you think about something like this that just has so much information in it, it seems, is to try to write out a chemical reaction piece by piece. In the Haber process, nitrogen and hydrogen are directly combined to form ammonia. We talked about word problems and how to go from word problems to actual chemical equations and then balancing them from there. Let's talk about nitrogen. Remember that nitrogen, and they gave you this because they're nice in this case. Nitrogen is diatomic because it ends in gen. Anything that ends in gen or ene is going to be diatomic. Remember Brinkelhoff. So nitrogen, with some unknown stoichiometric quantity, is combined with hydrogen and some other unknown stoichiometric quantity, N2 plus H2, to yield or create ammonia, which is NH3. Not to be confused with ammonium. Sometimes if I'm talking fast, I will say the wrong one, but just make sure you know the difference when you're thinking more slowly and carefully. There is the trick that I told my students about called the 2-3 switch trick. And the 2-3 switch trick is useful for a lot of the time when you have a diatomic element on one side that appears in a compound on the other side. So here's how the 2-3 switch trick works as a review. The 2-3 switch trick says, find your diatomic element that appears on one side and on the other side with a 2 and then a 3, or even another prime number set like 2 and 5. So you have H2 and then you have blah H3. The lowest common, and I'm trying not to get my math words mixed up, I think it's the lowest common multiple or something like that for hydrogen 2, and then the H3 would be 6. So H2 could become 6, putting a 3 here. The blah H3, you can get 6 hydrogens on this side by putting a 2 here. Once you get the 2-3 switch trick done, look at your other pure element, because your hydrogens are good. 6 hydrogens on this side, 6 hydrogens on this side. Your nitrogens actually auto-balanced themselves, so to speak, with using the 2-3 switch trick. So this is the 2-3 switch trick and how you actually balance the equation. Now you have the stoichiometric quantities as far as their ratios go. You want to find the picture that matches. So what we really effectively need to see is that for every 1 mole of nitrogen, we require 3 moles of hydrogen. So we want to find a picture or a diagram that represents 3 times as many hydrogen molecules as nitrogen molecules. If hydrogens are the little black sets of the pairs, and nitrogens are the larger white ones, we want to find ones that have twice as many of the black ones. So we have 1, 2, 3, 4, 5 hydrogens, and we have 1, 2 nitrogens. This doesn't work for us because we have 2 versus 5. That is not the same. We have 1, 2, 3, 4 hydrogens and 1, 2, 3, 4 nitrogens. that also won't work for us because 4 to 4 is not the actual ratio. This one also fails because we have more nitrogens than hydrogens. What does make sense is 1, 2, 3, 4, 5, 6, and then 1, 2. This is just like what we have. We have a 2 to 6 ratio. 2 to 1, and then 6 and 3. This actually does satisfy the conditions. Because 1 over 3 is the same as 2 over 6 as far as the ratio goes. So this one works for us. Thick-walled vacuum jar. So this is an example of a demonstration that I did. A lot of chemistry teachers do this. A beaker of water is placed in a large sealed jar that is attached to a vacuum pump. As air is pumped out of the jar, the water begins to boil. The water is not boiling because the temperature increased. We're going to say this is going to be a constant temperature process, which is termed isothermic. Now, what is causing this water to boil if the temperature is not increasing? I want you to think about the ideal gas law and the minor derivations from it. What causes something to boil? The temperature of the water decreases as the surrounding pressure decreases. That doesn't make any sense. The temperature of the water is never going to change in this process. The lower pressure inside the jar causes the water to contract. Quite oppositely, the water would expand due to the lower pressure in the jar because there's less pressure pushing on the water. Remember that pressure equals force over area. If there's less force, then there is less pressure, and the water is going to be more likely to vaporize. The air pressure in the jar has been lowered until it is equal to the vapor pressure of the water. This one seems like a plausible answer to us so far. At this particular temperature of the room, whatever it is, water has a certain vapor pressure. The pressure on the water is insufficient to hold the hydrogen and oxygen atoms together, resulting in a decomposition reaction. This is a physical phase change, not a chemical change. So the water is not turning into hydrogen and oxygen. Doesn't make any sense. This is a phase change. When water liquid turns into water vapor, it's still H2O. So the one that makes sense to us is that the pressure in the jar is lowered. Air is getting sucked out of the vacuum, or out of the bell jar, until the water has so little pressure pushing down on it that it can actually vaporize into a gas. And remember that boiling does not necessarily have to happen at a high temperature if it happens at a low pressure. And this next one is the last one that we're going to do in this video before I go to a next video, because we're already at 23 minutes. If you're finding that I'm taking a long time to explain things, that's kind of the point. You can watch these over a couple of different days, or break them up into pieces, or speed them up on YouTube by changing the settings on the gear. According to the periodic table of the elements, which elements belong to the same period? This one's really asking you to remember the difference between a period, which is basically a row, and a group, which is a column. Now, a group is also called a family. Family, not family. Family. And it's a column. It's asking about the same period. So you want to find things that are all in the same. We're going to color code this. You're going to find things that are all in the same row. So looking at the periodic table that I have pulled up on my laptop beside me, I see aluminum, germanium, antimony, arsenic, and gallium. Aluminum and gallium are in the same family, but they are not in the same period. So I know that gallium is next to germanium and is actually also next to arsenic. Antimony is SB and it's down there somewhere. Aluminum is Al and it's up there somewhere. The only ones that were carefully designed to be in the same period are these three. So on the SOL, you would actually select all three. Selecting two of the three or one of the three will get you no credit. That is the last one for this video. The next video will pick up after this.